Welcome to this eLearn security video lesson on PowerShell for Pentesters, Introduction to Leveraging WMI and Methods for Persistence. In this video, we're going to introduce Windows Management Instrumentation, or WMI, as it relates to PowerShell, and also a tool we can use for persistence via malicious WMI event subscriptions once access has been obtained to a machine. Windows Management Instrumentation, or WMI, allows for the management of Windows workstations, desktops, and servers both remotely or locally, and can also be managed through a number of scripting languages, which includes PowerShell. You may already be familiar with WMI through working with its command line interface, known as WMIC, the Windows Management Instrumentation command line. We can call it directly from a standard Windows command prompt, as can be seen here. For our purposes, however, we'll be using PowerShell to interface with WMI. First, let's open up a PowerShell console to demonstrate several use cases as they relate to penetration testing. We'll also run our PowerShell console as administrator, since this will give us access to components which we would not have access to as a standard user. Before we get into how we can use WMI for penetration testing, let's first cover one of its primary information structures. One of those information structures are known as namespaces, which are essentially collections of classes containing objects that we can interact with. Getting information about the various namespaces can be done with one of the more common commands we'll be using, which is the get-WMI object command let. Get-WMI object command let allows us to get information about the various WMI instances, classes, and related information. We can obtain help for our get-WMI object commandlet by using the get-help commandlet along with the commandlet we'd like to view help pages for, which in this case is the get-WMI object commandlet. We can also list all available commandlets related to WMI with the get-help-WMI command. As we can see here, all commandlets related to interacting with WMI are listed. The most common commandlets you'll probably use are the ones highlighted here. For this demonstration, we'll briefly cover the get-WMI object and the invoke-WMI method commandlets. We can easily explore all available namespaces and their associated classes with the get-WMI object, along with the -namespace and -class parameters. With the following command, we'll simply list all namespaces within the root CMI v2 namespace, along with all of the namespace classes. We can see that our command lists a lot of information regarding available namespace objects, but we can also refine our results by piping the results to the select-object commandlet and returning only the names of the namespaces. This will give us an easier to digest list of namespace objects, as we can see with the following command. Furthermore, we can also list all classes within a specific namespace, in this case, the root CMI v2 namespace, by using the previous command, but using the -list parameter. Of course, this returns too much information, so again, we can search for specific classes within a namespace by piping the results of the above command to the where-object commandlet, and can use the name property variable to return only results that match a particular string by also using the -match parameter. We'll do this and search for classes within the root CMI v2 namespace that contain the string win32_service. We can see this returns a list we can work with. So far, we can see how we can search for and get information about WMI namespaces and classes using various PowerShell commandlets and filters. If we want to get information about a specific class, the win32_service class for instance, we can use the get-WMI object commandlet and the -class parameter as follows. We can see the win32_service class returns a list of all services configured on the system. It's a lot of information, so again, let's further refine our PowerShell command to list only running services, again, with the where-object commandlet, but this time with the state property variable, and we'll use the -match parameter to match on the string running. We can see that with the previous command, we've returned only services that are in a running state. Furthermore, we can match on any of the properties. For instance, if we're looking for a service with defend in its name, we can use the name property for our variable. Now that we have a better idea of how we can explore WMI namespaces and classes, let's see how we can use WMI to our advantage during an engagement. One useful class we can use is the win32_process class. We can get specific information about a class's available methods by piping results to the get-member commandlet and using the -member type parameter and method name like follows. We can see that the previous command returns the methods available with the win32_process class, and that the available method is the create method. This method will come in particularly handy for us, as it allows us to create arbitrary processes using PowerShell and WMI, which will run as a child process of the WMI PRV se.exe process, which makes it beneficial in regards to executing processes through other, likely already trusted processes, also known as a whitelist bypass. Let's create a simple command.exe process using this class as an example. First, we need to create a variable to instantiate the win32_process class with get-WMI object commandlet. Next, we can use the win32_process_create method to create our cmd.exe process. Which, we can see, launches a command prompt. Furthermore, if we view our processes with Process Explorer, we can see that our command.exe process is running as a child process of the WMI prvse.exe process. As can be seen here. Although that is only one way to launch a process using WMI through PowerShell, there are other commandlets we can use to achieve the same. By using the invoke-WMI method, commandlet like follows, for instance. As you can see, we can use the invoke-WMI method commandlet to launch our process as well, and similarly, it will run as a child process of the WMI prv se.exe process as we can see here. Aside from being able to execute local commands with PowerShell and WMI once we've gotten access to a machine, we can also use these methods to launch processes on remote systems, assuming we have credentials. We can do this by appending the -computer name and -credential parameters along with the remote hostname or IP address, and username values as with the following command. We can initially confirm that the process was successfully executed on the remote machine by confirming that the process ID property contains a process ID. We can see our process as a process of 2512 in this case, and additionally, that the return value property contains a value of 0. A return value of 0 denotes our command was successful. To be absolutely sure our command on the remote machine has been executed, we can use the get-WMI object commandlet along with the -class parameter, specify the win32_process class while applying a filter for the process ID property, which was returned via our previous command, which was 2512. We also need to use the -computer name and -credential parameters as we did previously. As we can see, the remote system returned information about the process we previously executed, as we can confirm with the process ID. If we'd like to kill the remote process, we can quickly do that by using the same command as previously, but pipe it to the remove-WMI object commandlet like follows. And if we query for our previous process ID on the remote machine, we'll see we get no results as the process has been killed. Another way we'll see WMI and PowerShell used together is in the context of persistence. Of course, this is important to us as maintaining access is often an important part of our engagement scope. For this, there's a great PowerShell script known as PowerLurk that helps automate the process of creating persistence via malicious WMI event subscriptions. We can download PowerLurk from the following URL. Additionally, more information about this tool, as well as use cases, can be found at the following URL as well. We encourage you to read the blog post, as there's a lot of great information there. To replicate this attack scenario, we'll open up two SSH connections to our attacker system using PuTTY and run most of our scenario from there, while our current Windows system here will consider to be our target machine here. Let's open up two SSH connections to our attacker machine. We'll need a separate connection for a Python HTTP server. It's for this reason we're opening up two connections on our attacker machine for this demonstration. For this particular scenario, first, we're going to generate a payload with MSF Venom, which we will then download to the target system via a download cradle. We'll generate the payload first on our attacker machine. We've created a payload executable called payload.exe, as we can see here, and confirmed it is a 64-bit executable with a file command. Next, we'll use Python simple HTTP server to serve our payload to our target. Now, from the target machine, we'll use a PowerShell download cradle to download the payload into the C:/program data directory as a file named payload.exe on the target. Let's confirm our payload has been downloaded by browsing the C:/program data directory and confirming our payload.exe executable is there. We're not going to execute our payload just yet, but shortly we'll create a malicious WMI subscription event that will trigger our payload whenever the user launches a particular program. Before we do that, we should have a handler ready to accept the connection from our payload. On our attacker machine, we'll use a multi-handler and configure it with the same options we used to generate our payload. Now that we have our payload in place on the target and a handler up and running, let's make sure we're also hosting a copy of PowerLurk.ps1 script on our attacker machine. In this case, we have already downloaded it, and it is in the same directory being served by our Python HTTP server. Next, from the target machine, we're going to use the net.webClientDownloadCradle method with the download string function to call the PowerAlert.ps1 script along with its register-malicious WMI event function. The PowerAlert trigger we're going to use is the process start trigger. This trigger will generate our malicious WMI event every time the user launches the calc.exe program. From our target machine, let's execute our download cradle and execute our PowerAlert command. As part of our download cradle, we've called the register-malicious WMI event function from PowerAlert, and we defined a name for our malicious WMI event with the -event name parameter. For this demonstration, we used calcexec as the name of our malicious WMI event. We also used the -permanent command parameter, which we use to create a command that will launch our payload using command.exe. And finally, we set the -trigger parameter to process start. And lastly, use the -process name parameter to define the process we want to trigger our payload executable. In this case, we'll set the process name to calc.exe. We can confirm our malicious WMI event is in place by again running the PowerAlert script along with the get-WMI event function and the -name parameter. We can see here our new calcexec WMI event has been created, and we can also see that the command line template property contains our command to launch our payload. Now, it's only a matter of our user launching the calculator application which will trigger our payload executable. For demonstration purposes, we'll launch calc.exe on our target system, at which point it should trigger our WMI subscription event, resulting in a reverse shell back to our attacker machine. As we can see, when we launch Calculator, we have received a reverse shell back to our attacker system, and now can also confirm that we are the NT Authority system user by interacting with our session and running the getUID command. Keep in mind that PowerAlert offers a number of different ways to trigger our malicious WMI events. We encourage you to experiment with this tool and the different ways we can execute our payloads. As we can see, the ability to interact with WMI through PowerShell offers us some great advantage in regard to stealth and whitelist bypasses, as it is an excellent way to try and stay under the radar during engagements. From here, we would move forward with our post-exploitation tasks. And this concludes our video lesson on PowerShell for Pentesters, Introduction to Leveraging WMI and Methods for Persistence. Thank you for joining us.